Well. I can't really talk about circular motion without talking about universal gravitation and orbits in particular, because, that is a very common kind of circular motion in our universe. Now, unless you're one of these flat Earth nut jobs, then you believe that, as we have plenty of evidence to show, that things are going around other things all over the place in the universe. For example, the sun is at the middle of our solar system, and you can tell it's the sun because it has little rays coming out of it like this. And there's some planets like the Earth. So here is North America, South America, and then this other stuff. And it's going around in a circle. I'm going to make this might look like an ellipse to you, but it's the kind that's like it's further away and it's closer to you here. So that's a circle going around the sun like that. So if that's the case, well, we know that if there's circular motion, that the amount of unbalanced force toward the center of the circle must be equal to mv squared over r. And I'm going to tell you something about universal gravitation, about force in that situation. It's not really something that we can come up with experimentally. What I like to do, you probably have noticed, is to do like lab exercises at the beginnings of things, so to try to lead you to the point where you're like, oh, I think I see what the relationship is here, and then I'll tell you what it is in notes. But we can't really do that here because it's hard to measure things, and there's ways of doing it. But anyway, I'm just going to tell you that the force of gravity, and now I want you to notice that I'm going to use a big G here, not F little g, not like our local how much gravity is there like on you because you're here on planet Earth. This is like the universal gravitational attraction between objects out there in space. That universal, I'm not going to write this every time universal, but I'm going to write it here just to make sure we understand that that's what we're talking about, is what do you think it would depend on? Like how much force is there, attractive force between the sun and the Earth? You might think that it depends on the mass of those two objects, and you'd be correct. The bigger the thing is here, the more attraction there's going to be, and the bigger the thing is here, the more attraction. And it is true that it is directly proportional to both of those things, just to the first power, just like it is there. And you might also think that it depends on how far apart the objects are from each other. And that is also true. And the further apart they are, if you make that r bigger, then the attractive force between the things gets smaller. So that means that the r is going to be down here. Now in this, mv squared over r, it's r to the first power. With gravity, it's actually r squared on the bottom. It's directly proportional to what we say the inverse square. Inverse is on the bottom, and the square is the power. And then there's a constant here, because it's our universe. Just like our constant on Earth for our local gravity is about 10 newtons per kilogram. We always multiply by mass by 10, right, to figure out how much gravitational force there is. Here we have to multiply m1 times m2 divided by r squared. We have to multiply by this constant, and it's not so pretty this time. The constant is about 6.67 times 10 to the negative 11th. I'm going to write down what the units would have to be. If you think about it, if we're going to get force here, then this constant would have to be newtons, and then we would have to divide by kilograms and kilograms to get those to cancel out, and I'd have to multiply by meters and meters on the top. I don't really care that you ever write that again, but just for the correctness of your notes, I'm going to put the correct units there. Now, this is the constant. Show you a trick here. Uh-oh, where's my calculator? Hold on a sec. Let me go get my calculator. If you are using a TI 8384 type calculator, then you can do this. I'm going to go ahead and type in the number 6.67 times 10 to the negative 11th, and then I'm going to store, that brings up that little arrow there, that number as the letter G. So I'm going to hit alpha, and then tangent is, you can see a little green G right there, G, and I'm going to hit enter. Okay, and it just pops that number back out now. But now the cool thing is, whenever I bring up alpha G and I hit enter, that number is stored in that letter, just like setting a variable equal to something. So every time I do one of these problems, I don't have to type in that number again. I can just type in that letter G instead. So I recommend that you do that if you're using a calculator like this. I'll have some other recommendations for you too. Okay, so where do we go from here? So in this case where the Earth is moving around the Sun and there's this attractive force on the Earth toward the center, that must be equal to the unbalanced force. There is no other force on the Earth, just the one from the Sun. So that must be the thing that's keeping it moving in that circle. So that means that the unbalanced force toward the center of the circle must be equal to that force of gravity. In other words, these two things must be equal to each other. So that means M, and which M is this? This is the thing that's in orbit, right? This is the thing that's actually moving in the circle, is this thing. I have to be, I'm clarifying that because there's two M's here and I need to know which one is which. One of them's going to cancel out, one of them's not. So I've got mv squared over r, that's that. And then this is g m. There's one mass that's at the center, that would be like the Sun in this example. And then there's the other mass, which is the thing that's in orbit, over r squared. So I'm going to spare you the algebra because I know you know how to do algebra, but some things cancel out. And one of the things that we get, one of the results here, is if we solve for v, v is equal to the square root of g times the mass of the thing in the center over r. And just need to be careful here. In the case where we're talking about satellites orbiting a planet, like satellites, a lot of satellites are in what we call low Earth orbit. So this r right here, it's not the altitude of the satellite above the surface of the Earth. This is the distance from the center of one object to the center of the other. Of course, to the center of the satellite, that's not going to matter, but to the center of the Earth, that could make a big difference. So you've got to be careful. Make sure you've got the right r value there. Now, we'll put a little box around this. These are like the important equations, new equations that we have. Of course, those are going to show up. You're going to have access to those when you are doing homework or when you're taking the test, but you need to know how to use them. So we also know that for anything moving in a circle, that the speed of it is equal to the circumference of its circular path divided by how long it takes to go around. So we have two different expressions. We've got this new one right here for speed of something that's in a circular orbit, and I've got this expression, which is always true for all things. That's always true, right? This one is specific for orbits. Like if you've got some question about like a car driving around a turn and how much friction, and you bust out this thing, that is not going to work out well. That is specifically for orbits. But this is for all things moving in circular paths at constant speeds. So in this case, I should be able to set those two things equal to each other, right? Two different expressions for velocity. So 2 pi r over t, the period, is equal to the square root of g m over r. And I'm going to spare you the algebra again and show you that after you do some simplifying and so on, 4 pi, I wrote an r there, 4 pi squared, or g m times r cubed. And remember, this is the mass of the thing in the center. And if you're keeping score, you know how Newton has 3 laws. There's Johannes Kepler, who's another physicist, astronomer in particular, and he had 3 laws of planetary motion. This is Kepler's 3rd law, in case you're ever in a trivia contest and you need to know that. I'm not going to ask you. Kepler's 3rd. All right. That is what you need to know. And I think from there, I'm going to let you try the homework problems and refer back to these notes. But I will give you some advice here about how to use your calculator before you get started. I told you about the storing that in there. When you're going to have a lot of very big numbers in these problems, and having done this for many years, I have been around the sun many times, and I've been around the sun many times with first-year physics students who struggle with these kinds of problems, very particularly because they can't drive their calculators very well. So you don't want to be the person who does, like, let's say you're trying to do this, like figure out what the period is, and you've got all these numbers. And you don't want to be this person who does pi 4 and then pi squared, and then you hit enter, and then you do divided by. You don't want to be that person. You want to be the person who takes a very disciplined approach to this sort of thing and does something like, I'm going to go ahead and do my second, oops, that's the wrong button. I'm going to do F1, which I get to that by doing alpha, the green button, and getting to F1 right there. And one of the things that allows me to do, option number 1, is make a fraction. So I could put my 4 pi squared up there on the top of the fraction, and on the bottom I can put g times, and then the mass of the central object. Let's say if we were talking about the sun's mass is about 2 times 10. I'm going to use my exponential entry, EE. I'm going to use that notation, 2 times 10 to the 30th. That's about the mass of the sun. And the distance from the Earth to the sun is about 1, I'm going to put this in parentheses, 1.5 times 10 to the 11th meters. and then I would have to cube that. Right? So my point here is when you enter these things, you want to use the fancy functionality of your calculator to make it look like that expression so you can really see what's going on there. If you just if you keep hitting enter, you're going to fill up your calculator screen with a bunch of garbage, and it's really hard to tell if you're going in the right direction. So I could go ahead and hit enter there. Okay, now we're going to end up with lots of situations here where we get very big, sometimes very small numbers like this. So what does that even mean? Well, I just did this, so that is the period squared of the Earth going around the Sun. So what would I do with that? Well, I would have to take the square root of that, square root of my, instead of trying to type that in again, I'm going to do second answer right there, and that's my square root of that. And if those numbers are for real, I mean, I could say, okay, it's the answer is about 31.6 million seconds. Okay, but we might want to convert that into years or days or whatever. So to get this into that form, we're going to have to do conversions like this a lot too. Divided by 60, this is seconds, right? That will tell me this is now how many minutes. And then divided by 60 again will give me how many hours. And then divided by 24 will give me how many days. And there you go, 365 days. If you're wondering to yourself, well, wait a minute, how did you know, Mr. McGrath, that the Sun had a mass of 2 times 10 to the 30th kilograms and that the Earth-Sun distance is 1.5 times 10 to the 11th meters? How'd you know that? I mean, what's up with that? I will tell you those numbers will be given to you in problems when you need them. So there you go.